questions will be held on until you pause. And then we'll, of course, have a more elaborate Q&A session at the end.
Okay.
Okay, the YouTube is up, so we are live now.
Oh, cool.
So people join in then from all over the world.
Yes, indeed. We can already see folks from Europe, from India.
Right, right.
Yeah, I think we picked this slot to kind of maximize the online coverage.
The exposure, right.
But of course, we couldn't cover like the whole world.
So I've been personally following your work on quantum switches.
Mm-hmm.
So I've been working on classical switches for a while now. And in another line of work, I've been working on what I like to call as two-sided queues. And so I think this two-sided queuing model can be used in a quantum switch. So I've been thinking about it like on and off, but I haven't written down anything yet.
It turns out I've started to collaborate with Leandros Tassoulas.
Oh, I see.
On these problems. So
I see.
We'll see what comes of that.
Okay.
Hello, Philippe.
Hello, how are you doing?
Good. I'm going to talk about some of your work.
Yeah, where are you? At UMass or?
No, I'm in my, I'm at home.
Hi, everybody.
Hi.
So tell me when.
I guess we'll wait for a couple more minutes maybe.
Okay.
Because I see people are still joining.
Let's start the recording.
Okay.
A little bit earlier.
Okay, maybe let's get started. Good morning, everyone. Welcome to one more seminar in the SNAPP seminar series this spring. Today we have Professor Don Towsley from University of Massachusetts, Amherst. Professor Towsley is a distinguished professor in College of Information and Computer Sciences. He holds a he holds a BA in physics and PhD in computer science, both from University of Texas. And his research interests include network science, performance evaluation, and more recently, quantum networking, about which he'll talk today. He has received numerous awards. He's corresponding member of Brazilian Academy of Sciences, and he received the 2017 IEEE Koji Kobayashi Award and 2011 Infocom Achievement Award. He also received numerous Best Paper Awards, including 1998 IEEE Communication Society William Bennett Best Paper Award. He was also a co-founder and co-editor-in-chief of ACM Tompex Journal, and he served as editor-in-chief of IEEE Transactions on Networking and numerous other editorial boards. He also served as program chair for several conferences, including Infocom 2009. So today he's going to talk to us about quantum internet. Without further ado, so Professor Towsley, the floor is yours.
Well, thank you for the kind introduction, and thank you for inviting me to sort of give a talk here. I'm hoping that after you listen to me that you'll find that there's some really very, very exciting and interesting problems in having to do with quantum networking that might entice you to sort of think about it in the future. I've listed collaborators that have contributed to what I'm going to be talking about. Actually, I should mention, I noticed that one of my collaborators, Philippe Na, is in the audience. So I can always address the questions to him instead of me. But in any case, what I want to do is talk about the quantum internet. And the first thing is, why are we interested in this? And it turns out that there are just a number of very exciting, important applications that have been sort of allowed by quantum. For example, in security, which is the most mature, quantum can be used to essentially provide physically secure keys. And when you think of that, of course, you would like to be able to have, let's say, an Alice and Bob in different parts of the country to be able to do that. Right now, it's only done, let's say, with it in meter proximity. You need a network for that. Most of us know about Shor's algorithm, the ability to be able to factor large integers into prime numbers and how that could tremendously affect internet security. But right now, we don't have the quantum computers to do that. They're not large enough. And so the idea is that if we could connect a lot of small computers in the network, that we might be able to really harness Shor's algorithm and other algorithms like it. Turns out that it's very useful for big science kind of imaging problems, especially when you're peering into the universe using sensors that are scattered around the globe. And again, you can get tremendous improvement by using quantum, but that requires being able to interconnect everything. And it's also useful for getting very high precision clock synchronization. So what I want to do is first I'm going to give you a quick Quantum 101 tutorial, and then I'll tell you what some of the challenges are, and then talk about some of the work that we've been doing in the areas of routing and path selection and in analyzing quantum switches, and then I'll summarize. So let's begin with Quantum 101. And let's first of all review classical bits. As you know, a bit takes one of two values, 0 to 1, and it's physically represented by a two-state device. It could be like a light bulb on and off, or it could be a voltage circuit where either you have a high voltage or a low voltage, and each of those represent one value. So in the quantum world, we have an analog referred to as quantum bits or qubits, and they represent a two-state quantum mechanical system. And a canonical example of this is a photon, which can be polarized. And here I'm showing a photon polarized in the horizontal plane and another one in the vertical plane. And so what we can do is think of them as representing two states. And the canonical representation uses bracket notation that goes back to Pauli. And so the horizontal state we would represent as a ket 0. And you can think of it, it's just a column vector with a 1, 0. And the vertically polarized photon would be a ket 1 or state 1. And you can think of it also as a column vector, but 0 and then 1 in the second position. But it turns out, you know, when you look at that, you realize that the polarization could be in any plane, it could be in any angle. And so quantum bits introduce something that's not available using classical bits, namely what's referred to as a superposition of a state. And so here we have a qubit in state phi, and it's a linear combination of these two states, 0 and 1, where the coefficients, alpha and beta, are complex numbers that are normalized such that alpha squared plus beta squared is equal to 1. Okay, and you can think of 0, 1 then as really the basis for this system. And so here we're looking at a couple of polarized photons at 45 and 135 degrees, and they can be represented in this way. So I'd like to introduce the notion of measurement. And let me just say that because the polarization can take any angle, the qubit, you know, it's can be in any one of an uncountable number of states. And so it's interesting to ask what we can sort of learn about it. And so with a photon, well, what we can do is we can pass it through a beam splitter. Okay, and what the beam splitter will do is that the photon will either go straight through, or it'll essentially be reflected and it'll go up. And so let's say that we have this qubit in state phi, the superposition that I have there. We pass it through this beam splitter, and you're going to get one of those two outcomes. Either it's going to appear out the other end, or it's going to be bounced up. Okay. And anytime that you send a qubit with this superposition, one of those two things are going to happen, and not both of them. And what is known is that if you repeat this many times, the fraction of times that you're going to have it bounce up, and let's say we'll interpret that as 0, is going to be alpha squared. And the fraction of time that it goes straight through is going to be beta squared. And so the coefficients then sort of relate to the outcomes of these kinds of measurements. And this is the only thing that we can really learn about these qubits. Okay, now we talked about a single qubit, but we can have, let's say, 2 qubits. And with 2 qubits, there are 4 basis states. They can be in 0s or 1s or combinations. And we can talk about the state of these 2 qubits, let's say psi, and we can write it, it's a superposition state, and we can write it as a linear combination of these 4 basis vectors. And what I'd like to do is to introduce this idea of entanglement, which is really fundamental and importance in quantum. We say that 2 qubits are entangled when the state of one can't be described independent of the state of the other. Okay, and there's one canonical entanglement, which is sort of the single most important resource for quantum communications and networking, called the Bell state. And I have shown it down here. It's essentially the superposition of they're both being in 0 and they're both being in 1 with identical coefficients. Okay, so we have this Bell state. You can think of it, it's can be expressed as a tensor product, as I've done right here. And it's interesting to ask the question, well, what happens, let's say, if I do some kind of a measurement? I measure the first qubit, 0A, or let's say, think of A as Alice, so Alice's qubit, okay? Well, we know it's going to yield either a 0 or a 1. And what happens, though, is if it yields a 0, then B, or let's say Bob, when he measures his qubit, he's going to also get a 0, okay? On the other hand, if Alice measures a 1, then when Bob goes to measure his qubit, he's going to measure a 1. And so, of course, each of these occurs with equal probability. And so this sort of suggests a way that you can generate shared randomness across distances, for example. And so, as I said, it's really the basis of quantum communication, quantum computing, quantum key distribution. So what I'd like to do now is look at the situation where, let's say, Alice is at, let's say, one end of the country, Bob is in the other end of the country, and suppose that Alice has a 2-qubit superposition state, and what she wants to do is to transmit the second qubit to Bob. And, let's say the distance is L between. So she tries, and turns out that qubits are very fragile, and so let's say it gets lost. Well, what Alice can do is now regenerate a 2-qubit state and try again, and let's say it gets lost, and then she regenerates the state again and tries, and then perhaps it succeeds. And it turns out that the probability that you get a successful transmission, it decays exponentially in distance. And this is unlike what happens with classical bits, which will decay sort of polynomially. And so this introduces a big problem of how do you end up essentially, let's say, if you generate entangled qubits, how do you sort of disseminate them sort of across wide areas? And so what I want to do is introduce what's called a quantum repeater. And what we do is we place it in the middle. It has quantum memories to store qubits. And what we do is, in the first phase, we generate Bell states across these 2 links. Okay. And the probability of success then, in that case, is going to be larger because the distances now have been halved. And then in a second phase, the repeater does what's called an entanglement swap, which is really a measurement of those 2 qubits that are the endpoints of these link entanglements. And if that succeeds, it essentially propagates the entanglement to Alice and Bob. And one thing that's interesting is that the repeater does this, but the repeater doesn't know what the superposition state ends up being between Alice and Bob. And so now if you have Alice and Bob at long distances, you would just sort of put together a chain of these repeaters. You know, and the objective would be to connect Alice and Bob. The links would generate Bell states, And then the repeaters would do these entanglement swaps, these Bell state measurements. And if they succeed, then the Bell state, the entanglement is propagated to Alice and Bob. Okay. Let me stop for a second and ask if there are any questions.
Yeah, quick question. Is it apparent when there's a failure to everyone involved?
Yes, so there's this notion that of heralding these operations, and there are algorithms that will allow you to know when this succeeds, and so then they can proceed. Clearly, that's important if you want to really be able to use this.
Thank you.
I have a question.
Yes.
So if there are two links, you said that the probability of success of each of them will be e power minus alpha L over 2. But then to actually have a successful transmission, both of them should be successful. So if I multiply the probabilities, I'll end up getting e power minus alpha L.
Right. So what actually you would do, and I've sort of hidden this under the cover, is you would have a number of memories at the repeater. And so you would store one of them, while you're waiting for the other. And that has the effect of essentially increasing the probability of overall success. But you're right, if it turned out there was really just one qubit and you could only store one entanglement per link, what you say is correct.
Got it. Thanks.
Now, of course, this can fail. Let's say this link entanglement doesn't get generated or swaps fail. And so you do have, in this case, a exponential decay as a function of the number of hops. Okay, and so this is a plot of the logarithm of the let's say entanglement creation rate as a function of the number of hops between Alice and Bob. Okay, now just one last thing that you can think of this as also part of the review. Suppose Alice wants to send a qubit to Bob, not just, let's say, generate a Bell state, but it has a particular quantum information it wants to send. Then it turns out this can be done by creating an end-to-end entanglement and then using it to teleport the information. And just want to point out that this teleportation will always consume a resource, namely one of these entanglements. I'm just going to quickly go through what it looks like. So Alice has some qubit that she wants to transmit to Bob. We have a repeater in the middle. So the first thing that Alice and Bob do is we create link level entanglements. We do a entanglement swap, and that if it succeeds, gives us an end-to-end entanglement. And now we're going to see how that's used to actually allow Alice to send her qubit to Bob. So Alice then entangles her Bell state qubit with the qubit that she wants to send, performs a certain kind of measurement on those two. The measurement, as we see, always destroys the quantum state, and what you get out of it will be a couple of classical bits, and it could be 0, 0, 1, 0, 1, 1, depending on, because the measurement is random. Alice then transmits that to Bob. At this point, Bob has no idea what Alice's information is, but it turns out that he can use that classical information to determine what operation to apply on his qubit here that will then transform it into the qubit that Alice wanted to send. Okay, so now let's talk about a quantum entanglement network. we have a bunch of quantum switches. Think of them as repeaters, but they also have the ability to do switching. They're connected via lossy links. They have a bunch of quantum memories. And then basically the operation is that the links essentially form Bell states between pairs of memories. And then the switches perform Bell state measurements so as to connect these Bell states and propagate it to users. And so we could do that, let's say, over this path right here. Okay. So here are some of the challenges. There's a question of like, what kind of service to provide? Should you do entanglement distribution, which is what I've been talking about? There's another architecture where the network would just be used to directly transfer quantum information. I'm not going to talk about that. You have this question of like, how do you allocate resources? You need to share this among multiple users. What are the right paths to use? Lots of interesting questions about performance modeling. One thing that I'm not going to talk about, but I want to bring to your attention is the quality of the state can deteriorate over time. And so there's one of the performance metrics that's important here is what's called qubit fidelity. And so there's a need to be able to model that. From a networking perspective, there are interesting questions about what the data and control plane design should look like. How do you do measurements? How do you do managements? And what I'm going to do is I'm going to talk a little bit about work that we've done on resource allocation and on performance modeling. Okay, so let's start with routing and path selection. And I'm going to do this in the context of a 2D grid network. Okay, we have an Alice, we have a Bob. The links are probabilistic in that with probability P, they can generate successfully a link entanglement. And the question is, how should Alice and Bob use the network to generate end-to-end entanglement? They could just take the shortest repeater chain. And it's going to have some sort of performance where the entanglement rate degrades exponentially as the number of hops increases. And what we're going to see is that we can, of course, do much better using the other switches in the network. Okay, so let's talk about what these switches, these repeaters are doing. Their roles are to connect Alice and Bob. They're not going to hold entanglement too long. They need to make decisions efficiently, and they need to be able to do it using limited information about the state of the network. Clearly, they can't, Alice or this switch right here can't sort of query what's going on at Bob before it decides what to do next. And so the routing operation that's going to be used here, or switching operation, is really entanglement swaps. And so the question the switch has to ask is essentially which qubits or which Bell states is it going to perform an entanglement swap on. And so what I'd like to do is to talk about an algorithm that we proposed that's a heuristic that makes do using local information. I'm going to focus on a particular switch U connected to 4 neighbors. Recall that the probability of a link entanglement being successfully generated is P. So we're not going to have all of the links up. If U faces a situation where there's only one link entanglement, well, its decision is pretty clear. It should just go ahead and do, it can't do anything. If 2 links are up, then again, use decision is pretty simple. It only has one pair of Bell states that it can do an entanglement swap on, and so it should just go ahead and do that. If there are 3 links up, let's say between these 3 switches right here, then what we proposed was a distance routing algorithm where each of the nodes keeps track of its distance from Bob and from Alice, and then and U knows what those distances are. And so what U does is it determines which 2 links would sort of reside on the shortest path between Alice and Bob. And so it turns out in this case, okay, W's distance is 2.2 to Bob, V's is 2 to Alice, and the sum of that is less than using any other pair of nodes. And so that's what you would perform the swap operation on. 4 links up, you do the same sort of thing. You would figure out which 2 reside on what would be the shortest possible path if it succeeds. And in this case, it turns out that the shortest is connecting V and W. And then, of course, it shouldn't waste the other 2 link Bell states and should connect them. Okay, so how well does a local rule do? Here I have the same graph as before. We're looking at the distance between Alice and Bob in hops, number of hops, looking at the entanglement generation rate. The linear repeater chain is if Alice and Bob just use the shortest path, and which means that if it doesn't, let's say, succeed, it doesn't try anything else. I've included sort of an upper bound, which is, let's say, doing multipath routing using global information. And what I mean by that is the following. It turns out that determining the best set of routes is NP hard. But so what we did was we look at a greedy shortest path algorithm. You look at the state of all of the repeaters, and then you find the shortest path between Alice and Bob, and then you take the next shortest, and you can have up to possibly 4 paths between Alice and Bob. And so that gives you this blue curve, and it's interesting to see that you still suffer some exponential decay, but at a much, much lower rate than if you only use the shortest. And then finally in red is the performance of this distance routing algorithm that just uses local information. And it lies in between. Probably the important thing is that if you have 2 users separated by 10 repeaters, doing multipath routing with this local information can increase your entanglement generation rate by 2 orders of magnitude. This brings up the question, what if you have multiple flows? And so here I have a setting with 2 Alice-Bob pairs, and there are a couple of choices that we have here. We could just give all the resources to one pair exclusively, and maybe do time division multiplexing between the 2 users. So here I'm showing the capacity region. This is the rate for pair 2, rate for pair 1. These points here correspond to what the rates that they would get if they have exclusive use of the entire network. And the blue line is what they achieve if they do some sort of time division multiplexing between them. It turns out, and I'm not going to go into detail, let's say that all the resources have been given to pair 1. It turns out there are situations where a switch realizes that it cannot help, let's say, pair 1, but that it might be able to help pair 2. And by doing that, you can actually get a slight increase in the capacity region to this red curve. And then finally, of course, you can essentially just divide up the resources between the two pairs. And so pair 1 gets these switches, pair 2 gets these. And this yellow curve shows what the capacity region is in that case. And you get a huge win. We've looked at other configurations. This is sort of the best in terms of having sort of a large capacity region. You could have, let's say, Alice, the pairs sort of really sort of having to share some of the same resources, and the improvement is not quite so good. Any questions before I talk about a slightly different way of doing things here?
Alan has a question. He was asking, should we understand how you define distance?
Oh, okay. So distance can be anything that you want. In these curves, I think that what we took was the following. It was a 2D grid with everything equally spaced, and we used Euclidean distance. We could have used Manhattan distance, although it turns out it doesn't do quite as well as Euclidean. If you have an arbitrary network, well, there's been some sort of more recent work that has used as a measure of distance the quality of the entanglement that get generated between two pairs of nodes, and that seems to do well. Any other question?
I have a question. So I'm a little bit confused about why the rate is decaying exponentially for the linear repeater network. Because I thought that you said as long as there is storage at each switch.
Oh, okay. I neglected to say, in that case and here, we're assuming we only have one quantum memory per link per switch.
I see.
And so that's why we get this decay.
Okay, so this means that Alice and Bob can talk only at the instances when there is like a path.
That's right.
Okay.
Exactly.
Got it. Thanks.
Okay, so the problem that we run into here, it's sort of well illustrated by this example. I'm showing a situation where some of the links have successful bell states, and here's Alice, here's Bob, and we see that there is a path that goes all the way up there. But unfortunately, with this switch, it has also the choice of being able to connect to this switch, and potentially, in its mind, that's going to result in a shorter path. And so it essentially does this entanglement swap, and that leads to a failed end-to-end entanglement. So what we're going to do is instead of just looking at bell states, which are two-state entanglement, we're going to, it turns out that those can be extended to like 3 qubits, 4 qubits, and so on. There's something called an n-partite GHZ state. The GHZ stands for Greenberger, Horn, and Zellinger. And what it looks like is it's an entangled state on n qubits, and it's sort of the natural extension of the bell state. It's the all zero state and the all one state, both with the same coefficient in front. And so from the point of view of a switch, suppose that there are 3 successful link Bell states that have been created. What it can do is what's called a GHZ measurement that can then propagate the entanglement to these 3 nodes. Okay. And when you do that, then this situation that arose and where we failed, what we would do instead is we would do a 3-way measurement. And in that case, we will connect Alice and Bob. Okay. And what's interesting is in terms of sort of evaluating the performance of this, it reduces to a percolation problem. And so what I'm showing here is the following. We're looking at a space where I'm varying the link success probability, and it's possible for the measurement to fail. So I'm going to have a measurement success probability Q. And the space is going to divide up into regions where when P and Q are not large enough, you don't have percolation. And when it is large enough, you do. And so if you use a 4GHZ protocol where you measure up to 4 entangled links when they happen, then you get a percolation region that's defined by this dashed purple curve. Any point in here corresponds to you have percolations and that you generate an infinite size connected component. And what that translates to is that you get distance independent entanglement rate, unlike the exponential decay that we've been seeing. If you only allow measurements up to 3 entangled links, then that percolation region gets smaller. It's defined by this right here. It's interesting that it turns out that there are situations where having more reliable measurement devices can actually lead to worse performance, which is indicated here. And so this is the graph from the previous slide. Here, we're looking at entanglement rate as a function of distance between Alice and Bob, and this is number of hops. And we're looking at different values for the link success and measurement success probabilities. The blue is the most reliable, and what we see is that we essentially get an entanglement rate that's very close to 1. And that is does not depend on distance. Whereas when those probabilities are low, what we're seeing is that as the distance gets larger, the entanglement rates essentially go to 0. And so going back to the example that we had before, here was a situation where just doing an entanglement swap could lead to a failure. But once we decided to allow for sort of 3 GHZ measurements, then we were able to get a successful end-to-end entanglement. Any questions before I go on? Okay.
Alan has a couple questions, I guess.
Sure.
Do you want to go ahead and ask Alan?
Yeah, I just had one question, actually. Are these 3 and 4 GH links more costly somehow?
Okay, so I'm not a device person. I've been working with a device person at MIT, and And, we're always asking him that question, and he always answers that it's not that much more costly to do these kinds of measurements than two-state measurements. So he keeps he keeps reassuring us that it's reasonable.
Thank you.
Don, this is Anastasios Giovannis from Sorbonne University.
Yes.
A small question that relates to all of the routing schedulers that you proposed. Since the end-to-end path is important, wouldn't it make more sense somehow to use information further on than just local information?
The answer is absolutely yes. The problem is that the timescales that we're talking about in terms of creating these paths are much, much smaller than the time it would require to gather that information.
Okay, this is exactly what I wanted to ask next. So yes, this answers completely my question. So it's actually a problem of timescales.
Right, exactly. It turns out that once you add more and more memory, then you can hold on to these for longer periods of time. And then you should, in fact, I have a student that I'm working with that's looking at how you can take advantage of that to be able to get more information before you actually make your decision.
Could you, I'm sorry to take your time, could you enlighten us on the period of the duration of this memory realistically today?
Okay, so there are two things going on. So memory coherence times, depending on the technology you use, it can be microseconds to a second. The issue here is that you're generating entanglement at, let's say, on the order of, well, we'd like to think on the order of microseconds, whereas the propagation delays, the times it would take to gather the information might be in the order of milliseconds. And so that's really the disparity that affects us.
Okay, thank you very much.
Okay, so I want to talk about quantum switch. First of all, so we have a quantum switch with, let's say, 4 interfaces. It's going to have a bunch of memories for loading and for doing readout measurements from. It has to have the capability of doing quantum measurements, Bell state measurements, or 3 or more qubit measurements. It has to have some logic. So in some sense, it's sort of like a small quantum computer. It turns out there are settings where it's useful to generate ancilla qubits. And so it will have multi-photon entanglement sources for doing that. And then, of course, it has to support classical computing and communication. And so what we've been interested in is trying to understand the capacity of, let's say, one of these switches. And we started off in the case where the switch is just serving Bell states and that all pairs of users are interested in Bell states. And here we sort of put on our classical network modeling hats. Okay, so we assume Bell states across links are generated according to Poisson processes. The rates can vary from link to link. The switch can store B qubits, and Bell state measurements succeed with a probability Q. And then it turns out in that case that there's a very simple birth-death process that you can use to characterize what's going on. And in the case where you have infinite amount of memory, you get a very simple, trivial expression for the capacity, the aggregate end-to-end entanglement rate, and it's easy to interpret. you need two resources, two links. That's where the two comes from. You're generating link entanglement proportional to the number of links you have, proportional to, let's say, the link entanglement rate. And of course, the probability of succeeding is Q. And you get also a very simple expression for the expected number of qubits that you have to store in this case. I guess I didn't mention, this is when all the links are identical. It's easy to handle link heterogeneity. And again, you can write down what the continuous time Markov chain is. It's sort of, I find it sort of cute that what you have is essentially a whole bunch of birth-death chains that are just attached at one node, one state where there's nothing in it. And so this is very easy to solve. Just to give you an example, here's a switch with 3 links. We're looking at capacity as a function of buffer size. The blue curve is when you have infinite buffer, so that's the best you can do. And in the red curve is showing the dependence of the aggregate capacity as a function of buffer size. Here, one of the links is almost twice as fast as the other 2 links. And what you see, then you can imagine, is the mismatch in the speeds essentially causes the need to be able to store entanglements for that link. We've looked at the case where you're serving not just, instead of Bell states, n, let's say GHZ states. And for the case of a homogeneous system, after a lot of complicated calculations, we came up with, the sort of obvious, simple expression for capacity. It looks just like for Bell states, except that we have n in the denominator because you need to gather n link resources to generate an NGHZ state, and a very simple expression for the expected memory that's used. We've looked at the case, a situation where the switch is serving both bipartite and tripartite state. And here, what motivated us was clearly you can do time division multiplexing and sort of switch between serving bipartite and tripartite, in which case you get something that looks like the following. We're looking at the capacity region. C2 is capacity for bipartite, C3 for tripartite. The endpoints here correspond to the performance you get if you only serve bipartite or only serve tripartite. If you do time division multiplexing, it's this dashed line. But by using sort of a very simple randomized policy, you can extend this region out. The blue corresponds to the case where you only have 1 buffer per link. The red where you have 3 buffers per link. So this brings me really to the end of the talk. I've mentioned, well, I've given you a little bit of an overview of quantum, mentioned what I think are some of the sort of broad challenges in quantum networking, and tried to sort of illustrate some of the issues, let's say, through some of the work that we've been doing here. To summarize, one thing I focused on was really generating and distributing entanglement across end users. And it turns out one reason for doing that, actually there are 2 reasons. One, it appears that that kind of an architecture is going to be easier to generate and to deploy than one that focuses on transmitting quantum state from, let's say, point A to point B. But the other is, I think that an architecture where you're transferring quantum state, that looks a lot more like classical networks. And so in some sense, it's not quite as interesting to me. And so it's made looking at networks that generate and distribute entanglement much more interesting. Quantum networks introduce new problems and old problems with new wrinkles. You know, I was having a conversation before we started the talk, and the scheduling problem in a, let's say, an entanglement generation switch, you know, bears similarity to scheduling problems in classical communication switches. There's a need for performance models to try to characterize capacities, latencies, and something that is really important in the quantum world, and it's not something that we think of, we have to worry about in the classical world, is the quality of the resulting state that, let's say, Alice and Bob generate using a metric like fidelity. Resource allocation looks really interesting. The distribution and management of entangled state in a very noisy environment. I didn't really talk about it, but you know, quantum state is very fragile, and so that makes it really challenging in terms of trying to maintain its quality. I think there are going to be interesting problems in terms of what the control architecture should look like. It's going to be hybrid quantum classical, at least for the start, and you know what that should look like. And network management. I've been working with some colleagues from the University of Oregon. We're trying to see how we can combine ideas from quantum process tomography with classical network tomography. And I'll just end by saying that, you know, the research on quantum networks really is in its infancy, and there are just a lot of exciting problems. And although I didn't write it down here, it's incredibly multidisciplinary. You know, we talk about in, let's say, wireless networks, we work with information theorists and communication engineers and mathematicians. Here, we need to work with physicists in addition to everybody else. And so I'll stop here and take questions.
I have a question.
Go ahead.
Yeah, so how you do time synchronization in a quantum network? Like in current networks, we do time synchronization using IEEE 1588, for example.
Right.
How we can do time synchronization in quantum networks to support the application that would that are time sensitive.
Right. So, you know, to be honest, I don't know how, what the sort of the schemes are that have been proposed. And actually, you know, you mentioned in the context of time sensitive applications, but I think it's much more challenging in a quantum network just to do synchronization, let's say between nodes. Even forgetting whether you're worried about time-sensitive applications. And honestly, I don't know what the ideas are there for doing that.
I have been doing some digging into this area, and I haven't seen much actually. So I think this is one of the areas which require further research.
I agree. Where I have sort of seen some work going on is, you know, it's clear that you're going to need to do both quantum and classical communication to support networked applications. If nothing else, you can think of it, you're going to have a classical header that's going to contain like routing information and whatnot. And it's going to be going on a, let's say, a separate wavelength from the quantum information. And all I know is that it's considered to be much more challenging to synchronize that than synchronization in just a pure classical network.
But in quantum networks, the two nodes or two switches can talk using quantum entanglement, right? We don't have to have links, right?
Oh, you do. I'm not sure what you mean by link. So you're going to have an optical fiber connecting them, because what the way that you generate the entanglement is, let's say, one node essentially entangles a photon and an atom or an electron, and then transmits that photon to the other node.
Ah, got it. So it only works.
There are other ways of doing that, but that's one.
Yeah, yeah, exactly. They were just talking about objects talk to each other without even any physical links between them.
Right. You can do free space.
Yeah, free
And
space,
I think
exactly.
in the atmosphere, the performance is really bad. But that's there's a lot of work going on in terms of like doing quantum satellite communication. And there, of course, it's going to be free space communication.
Yeah, and I agree with you. In this case, time synchronization will not be easy.
No, the sense I have is that it's really probabilistic, in that most of the time things don't happen simultaneously, but sometimes they do, and then you're able to, let's say, generate a Bell state, and you can do it in a way